Now it's time for types of reactions. I'm just reading straight from the textbook here. This isn't me coming up with this. This is just, let's see here. Prentice Hall Chemistry by Wilbraham, Staley, Matta, and Waterman. Waterman. I guess Waterboy grew up in Waterman. My mama said water's best. Anyways, decomposition reactions. When mercury 2 oxide is heated, it decomposes or breaks down into two simpler compounds, as shown in figure 11.6. You guys can't see figure 11.6. Well, it says here, 2HGO decomposes into 2HG in a liquid state plus O2 in a gaseous state. A decomposition reaction is a chemical change in which a single compound breaks down into two or more simpler products. Decomposition reactions involve only one reactant and two or more products. The different products can be any combination of elements and compounds. It is usually difficult to predict the products of decomposition reactions. However, when a simple binary compound such as HGO breaks down, you know that the products must be the constituent elements Hg, mercury, and O2, molecular form of oxygen. Most decomposition reactions require energy in the form of heat, light, or electricity. Single replacement reactions. By the way, I apologize for my voice. I'm recovering from the flu. My throat's messed up. So, bear with me. Single replacement reactions. Dropping a small piece of potassium into a beaker of water creates the vigorous reaction shown in figure 11.7. The reaction produces hydrogen gas and a large quantity of heat. The released hydrogen gas can ignite explosively. So, yeah, I knew that. That's interesting. So it says here, 2K in solid state, S for solid state, plus 2H2O, meaning liquid state, reacts to form 2KOH in an aqueous solution, plus H2 in gaseous. Similar but less spectacular reactions can occur. For example, if you drop a piece of zinc into a solution of copper nitrate, this reaction occurs. It says here, solid zinc plus copper nitrate in an aqueous solution yields copper in a solid state plus zinc nitrate in an aqueous solution. So basically, the zinc and the copper switch places. The two nitrates stay the same. Makes sense. It has something to do with the activity series of metals. Where the higher it is on the activity scale, if it's higher than the starting metal, if it's, for example, copper is below zinc on the activity series, or the reactivity series, I guess. So copper basically is like, okay, zinc, you can take my place. And then copper just sits there all alone, and zinc mingles with nitrate. Anyways, these equations describe two examples of a single replacement reaction. A single replacement reaction is a chemical change in which one element replaces a second element in a compound. You can identify a single replacement reaction by noting that both the reactants and the products consist of an element and a compound. In the equation above, zinc and copper change places. The reacting element, zinc, replaces copper, and the reactant compound, copper NO32, meaning copper nitrate with two nitrates. The products are the element, copper, and the compound, zinc nitrate. Whether one metal will displace another metal from a compound depends upon the relative reactivities of the two metals. The activity series of metals given in Table 11.2 lists metals in order of decreasing reactivity. Alright, well, I basically explained that part. I'll read the activity series of metals starting from the top, meaning the highest, to the bottom, meaning the lowest. Starting with lithium, potassium, calcium, sodium, magnesium, aluminum, zinc, iron, lead, hydrogen, copper, mercury, silver. So, silver is the lowest, and lithium is the highest. A halogen can also replace another halogen from a compound. The activity of the halogens decreases as you go down Group 7A of the periodic table. Fluorine, chlorine, bromine, and iodine. Bromine is more active than iodine, so this reaction occurs. Bromine in an aqueous solution, molecular bromine, I should say, meaning two bromine atoms attached, plus sodium iodide in an aqueous solution yield sodium bromide in an aqueous solution, plus 2 iodide, molecular iodine in an aqueous solution. But bromine is less active than chlorine, so this reaction does not occur. And the reaction it says that does not occur is bromine in an aqueous solution plus NaCl, which is sodium chloride in an aqueous solution. So that does not happen because it's already where it should be. There's no switching to go. Double replacement reactions. Sometimes when two solutions of ionic compounds are mixed, nothing happens. Other times, the ions of the two solutions react. Figure 11.8 shows that mixing aqueous solutions of potassium carbonate and barium chloride results in a chemical reaction. A white precipitate of solid barium carbonate is formed. Potassium chloride, the other product of the reaction, remains in solution. This is an example of a double replacement reaction, which is a chemical change involving an exchange of positive ions between two compounds. Double replacement reactions are also referred to as double displacement reactions. They generally take place in aqueous solution and often produce a precipitate, a gas, or molecular compound such as water. For a double displacement reaction to occur, one of the following is usually true. One of the products is only slightly soluble and precipitates from solution. For example, the reaction of aqueous solutions of sodium sulfide and cadmium nitrate produces a yellow precipitate of cadmium sulfide. And it says here the formula is sodium sulfide in an aqueous solution plus cadmium nitrate in an aqueous solution yield cadmium sulfide plus 2 sodium nitrate in an aqueous solution. 2. One of the products is a gas. Poisonous hydrogen cyanide is a gas produced when aqueous sodium cyanide is mixed with sulfuric acid. 2 sodium cyanide plus hydrogen sulfide, or sulfate, yields 2 hydrogen cyanide. Ooh, that's bad. Ooh. Plus sodium sulfate. Yeah, hydrogen cyanide is bad. 3. One product is a molecular compound such as water. Combining solutions of calcium hydroxide and hydrochloric acid produces water. CaOH in an aqueous solution plus 2HCl yields calcium chloride and water. Combustion reactions, my favorite. The flames of a campfire or gas grill are evidence that a combustion reaction is taking place. A combustion reaction is a chemical change in which an element or a compound reacts with oxygen, often producing energy in the form of heat and light. A combustion reaction always involves oxygen as a reactant. Often, the other reactant is a hydrocarbon, which is a compound composed of hydrogen and carbon. The complete combustion of a hydrocarbon produces carbon dioxide and water. But if the supply of oxygen is limited during the reaction, the combustion will not be complete. Elemental carbon, soot, and toxic carbon monoxide gas may be additional products. The complete combustion of a hydrocarbon releases a large amount of energy as heat. That's why hydrocarbons such as methane, CH4, propane, C3H8, and butane, C4H10, are important fuels. The combustion reaction for methane is shown in Figure 11.9. Gasoline is a mixture of hydrocarbons that can be approximately represented by the formula C8H18. The complete combustion of gasoline in a car engine is shown by this equation. 2C8H18, or that's 2-octane in liquid. What's it called? Liquid. It's just liquid. I'm sorry. I'm stupid right now. And 25 oxygen molecules yield 16 carbon dioxide and 18 water. The reaction between oxygen and some elements other than carbon are also examples of combustion reactions. For example, both magnesium and sulfur will burn in the presence of oxygen. As you look at these combustion equations, notice that the reactions could also be classified as combination reactions. 2 magnesium in a solid state plus molecular oxygen in a gaseous state yield 2 magnesium oxide in solid state. Sulfur in solid state plus molecular oxygen, gaseous state, yield sulfur dioxide, gaseous state.